Okay, on example 3 here, we're going to analyze a polynomial function. So in this example about pilots, the total number of certified pilots in the United States is approximated by a function of x, which is equal to 0.0000903 x to the fourth minus 0.0166366 x to the third plus 0.762 x squared plus 6.317x plus 7.708. Quite a mouthful. Where x is the number of years after 1930 and f of x is the number of pilots in thousands. Okay, so your input of this function is what year you're on after 1930, and your output is your number of pilots in the thousands. Okay, so we want to graph the function and describe its key features over the relevant domain. So using series of example x values starting at 0 and moving upwards, we get a series of data points. So every 10 values of x have been plotted here, and those plots have been connected with a smooth curve. Okay, so if you look at that data, it looks like we rise upwards, we hit a relative maximum, we fall downwards, hitting a relative minimum, after which we rise upwards as we continue out. Okay, that arrow upwards means that we continue going up at the end forever. We never come back down. We have graphed the important turning points, and anything after that is going in the same direction. Okay, so we want to describe the key features down here. The domain and range of the function is all real numbers. Because the function models years after 1930, the relevant domain and range are what? Okay, so they're saying the relative domain, the domain and range of the function is all real numbers. So the function that we described with all those big numbers in it, that didn't say anything about certain years, but the relevant domain and range are the ones we put on the graph. So we're just interested in looking at years after 1930. There are not a bunch of pilots before 1930, so there's not really a reason to put those dates on our graph. So we've constricted our graph to everything where x is greater than 0, right? Everything greater than 0 on the x-axis. And where do we begin? Well, we begin at 7.708. On the graph, it kind of looks like we're down at 0, but that's just because our increments are very large. There are 100 on each little box on the y-axis. But in reality, we're not starting at the origin. We're starting at 7.708 and all of our outputs of the function. So f of x is always greater than 7.708. Looking on the right side of the screen, this continues on to the next page of the book. So there is a relative maximum. It's not letting me write on this side of the page. Okay, well, you're just going to have to listen. So on the right side where it says there is a relative, we'd be saying maximum between 1980 and 1990. So they're talking about right in here. And there is a relative minimum between 2010 and 2020. Right in there. So we've identified the extrema. The end behavior as x approaches infinity, so as we move this way on the x-axis, our function approaches infinity as well. So we're approaching larger and larger values for our output, as denoted by that arrow here at the end. Okay, it's heading upwards to infinity. Okay, intercepts. Well, in the relevant domain, the y-intercept is at 0 and 7.708. So that's that starting value. That is our y-intercept. There is no x-intercept, or 0, because the function begins at a value greater than 0, and as x increases, the function increases. So we were never down at a value of 0, and we only increased from there. We came back down for a moment, but then we increased. We never had an x-intercept on this graph. Looking at the idea of symmetry, is there any symmetry in this? I would say no. The graph of the function does not have any symmetry at all. There is no way that you could draw a line through this graph where you'd have some sort of symmetrical image on the right and left. You'd have some mirror image. Doesn't matter if it's a vertical line or a horizontal line, neither one could be done on this graph. So this graph does not have any symmetry at all.